rest of the lecture is going to be to prove corollary 42 in section 13.6, which is the degree over Q of the nth cyclotomic field, Q adjoins zeta of n, is phi of n, the Euler phi function. That is written as a mathematical equation. The degree of Q adjoins zeta of n over Q is phi of n. All right, so we already saw this for n equals p, the special case where n is prime. And how did this argument work? We saw that zeta p, a pth root of unity, primitive pth root of unity, satisfies this polynomial phi p of x, x to the p minus 1 plus x to the p minus 2 plus x plus 1. And we know, we showed way back when we were talking about polynomial rings in Math 206b, by applying Eisenstein's criterion to phi p of x plus 1, that phi p of x is irreducible in Q bracket x. So zeta p satisfies this monic irreducible polynomial of degree p minus 1. So that polynomial is the minimal polynomial of zeta p. All right, so the degree of the minimal polynomial is the degree of the field extension Q adjoins zeta of p over Q. So this has degree p minus 1, which is Euler phi of p, the number of numbers less than p that are relatively prime to it, number of positive integers. So if we want to compute the degree of the nth cyclotomic field over Q in general, we're going to need to know what is the minimal polynomial of a primitive nth root of unity over Q. Really, all we need to know is what is the degree of this minimal polynomial, but we're going to figure out what the degree is by finding what this polynomial is. That is, we're looking for a monic irreducible polynomial in Q bracket x that has zeta n as a root. Okay, so let me first back up and talk a little bit about what we know so far about nth roots of unity. What is this field, Q adjoins zeta of n? It's a splitting field for the polynomial x to the n minus 1 over Q. This polynomial is separable. Q is characteristic 0, you take the derivative, and it's clear that this polynomial is relatively prime to its derivative, which is just n times x to the n minus 1. So what does that mean? It has n distinct roots in this splitting field. So these roots of x to the n minus 1 in this splitting field are the nth roots of unity. We saw before that they form a group under multiplication. If you multiply two of them, you get another one. If you take the inverse of one of them, you get another one. So we let mu of n, mu sub n, denote this group of nth roots of unity. This is a finite subgroup of the multiplicative group of a field. So it is cyclic. So a generator for this group is called a primitive nth root of unity. And we're just going to name one primitive nth root of unity. The symbol zeta sub n is used to denote a primitive nth root of unity. Okay, so in terms of this one primitive nth root of unity, mu of n, mu sub n, the nth roots of unity, are just all of the powers of zeta n, where it's zeta n to the a, where a goes from 0 up to n minus 1. And which of these powers are the primitive nth roots of unity? They're exactly the ones of the form zeta n to the a, where a is between 1 and n, and the GCD of a and n is 1. How do you see that? Well, we're in a cyclic group of order n. We know that zeta n to the 1 has order n, and we know a lot about the order of the powers of an element in a finite cyclic group. All right, so from this description, it's very clear that there's exactly phi of n, Euler phi of n, of these primitive nth roots of unity. And okay, so we know that mu sub n, this group of nth roots of unity, is a finite cyclic group of order n. So it's isomorphic to z mod nz. And what is one isomorphism between z mod nz and mu of n is this isomorphism that takes the integer a, or the element a in z mod nz, to zeta n to the a. So I'll pause and erase And now that we've recalled some basics about nth roots of unity, we'll dive more deeply into nth roots of unity and give a sketch of how we're going to prove this result about the degree of the nth cyclotomic field over Q. Let's continue with a basic observation about how nth roots of unity relate to dth roots of unity for divisors d of n. If d is a divisor of n and zeta is a dth root of unity, then zeta is also an nth root of unity. Why? Well, what is zeta to the n? It's zeta to the d to the n over d. And zeta to the d is 1 because zeta is a dth root of unity. So 1 to the n over d is 1. Okay, so it's important for n over d to be an integer for this to even make sense. So what does that mean? The group of dth roots of unity is contained in the group of nth roots of unity for each d dividing n. So let's think about a kind of converse. So let's look in, so this should be, if zeta is an nth root of unity, what is its order in this group of nth roots of unity? So it's in this finite cyclic group of order n. So by Lagrange's theorem, it has to have order dividing n in mu n. So maybe it has order n, and then it is a primitive nth root of unity. But if it's not, then it has to be a primitive dth root of unity for some d dividing n. That is, it's going to generate a subgroup of order d for some divisor d of n. So I find that to see what this is saying, it's helpful to think about an example. If you think inside the complex eighth roots of unity, I is an eighth root of unity. If you take I to the eighth, that's I to the fourth squared, which is 1 squared. But it's not a primitive eighth root of unity. It doesn't generate this finite cyclic group of order 8. It only has order 4. It is a primitive fourth root of unity. So how do you see like which? It's a primitive dth root of unity for some divisor d of n. Which divisor? Whatever the order is of this element in mu n. Okay, so now we're going to give the big definition for this video. The nth cyclotomic polynomial phi sub n of x is the polynomial in q adjoins zeta n bracket x whose roots are the primitive nth roots of unity. All right, so it's defined as a product by, we're saying what the roots are. So the roots are these linear factors. You have a product over each zeta in un that is a primitive nth root of unity of x minus zeta. And we know how to describe all these primitive nth roots of unity. We start with one primitive nth root of unity, zeta n, and we take the 8th power of it, where a is a positive integer between 1 and n that is relatively prime to n. So it's a product over all a between 1 and n such that the GCD of a and n is 1 of x minus zeta n to the a. Okay, so it is very clear that this is a monic polynomial of degree equal to the number of primitive nth roots of unity, which is phi of n, Euler phi of n. And zeta n, this one primitive nth root of unity, is a root of this polynomial. So what we would like to say is that, in fact, this nth cyclotomic polynomial is the minimal polynomial of zeta n over q. But what is the minimal polynomial of an algebraic element over q? It's a monic irreducible polynomial in q bracket x that has this algebraic element as a root. But the way that we define this polynomial, it's clear that its coefficients are in q adjoins zeta n. But if we want this to be the minimal polynomial of zeta n, then they better be in q. So what we're going to prove in this lecture first is that the coefficients of this nth cyclotomic polynomial, not only are they in q, but they're actually in z. So we'll prove that first. And then, okay, so this is now a polynomial in q bracket x that is monic of degree phi of n. What else do we need? Oh, that has zeta n as a root. what else do we need in order to say that it's the minimal polynomial of zeta n? Is that we need it to be irreducible in Q bracket x. So we're going to show, this is lemma 40, then theorem 41, that the nth cyclotomic polynomial is irreducible in Q bracket x. So these two facts together show that the nth cyclotomic polynomial is the minimal polynomial of zeta n over Q. So the degree of this polynomial, phi of n, is the degree of Q adjoins zeta n over Q. So that is phi of n. So the corollary 42 that we started this video with follows directly from this lemma and this theorem. So that's the goal for the rest of this lecture. But before jumping in and proving these results, I first am going to want to talk in the next video a little bit about how do you actually compute these cyclotomic polynomials.